Hey, you discontinuity, get out of here. We're going to remove some discontinuities. And the best way to remove them is to reassign values, but we can only do that if they are, well, removable. So let's do it. The graph of f of x is above. State the x value of each discontinuity until if the discontinuity is removable, non-removable, or vertical asymptote. If the discontinuity is removable, state the logical value of f of x that would make the function continuous at that point. Like, what? Okay, just stop. Let's start driving our cars. Let's pick a color, green. I'm just going with green. I'm feeling green today. So we are going to find every x value of a discontinuity first. We'll classify them later. So we drive a car, boom, 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 boom. No! Okay, we have a discontinuity at x equals -2. We will classify it later. All right, we jump back on the road somehow. We have another life, and we drive, and then, oh, we had a pothole. We broke down. So we have a discontinuity at x equals -1. There we go. I'm writing them down here as we say them. So far, we have found the discontinuity at -2, -1. You're probably way ahead of me on this. And we keep driving, we keep driving, we keep driving. Boom, there's another one. It's at 3. And then we just fell off a cliff there, and there's a sheer cliff on the other side. It goes infinitely far down, infinitely far up. What kind of cliff is this? I don't know, but it exists at x equals 4, okay? So now let's do the rest of the directions where it says tell if it's removable or non-removable or a vertical asymptote. Now technically vertical asymptotes are non-removable, but they are kind of in a class all to themselves. A lot of people classify them that way. So let's just go for the obvious. This one is a vertical asymptote, x equals 4. And I would like to think that's obvious. Let's zoom out a little bit. You'll be able to see it a little better. There we go. See more things all at once. So this one's a vertical asymptote. And this very first one we encountered was where the limit does not exist. Okay, notice that the limit as I approach an x value of -2 from the left and from the right are two different y values. So that makes x equals -2 non-removable, meaning that I can't look at you and say, hey, you know what, if x equaled such and such, then this would not even be discontinuous there. Like, we'd have continuity. It's not going to happen. But here we have a removable discontinuity, and here we have a removable discontinuity because as we approach from the left and from the right, we approach the same y value. So the limit exists for these, and that is what makes them removable. So these are removable. You can abbreviate if you want. I choose not to because this pen is wonderful. I enjoy writing with it. And then, if it's removable, state the logical value of f of x that would make the function continuous at that point. And I don't want to just write f of -1 equals, I want to put it in context. So f of -1 equaled, well, if this dot was up here, we wouldn't have a discontinuity, and that would be 1. Would create continuity. I like to explain my thinking. And we're going to do the same thing for this one. And if f of x, it doesn't even exist. I mean, the function is undefined, I meant to say. The function is undefined, but if we defined it at 3, f of 3, it would be -1. And that's the same explanation here. It would create continuity because that's what we were trying to do anyway. Continuity. Done.